So what are you going to learn about in this video? We are going to learn, or you're going to learn, that there is a mass difference. More importantly, some missing mass, which happens during fusion and fission. You will also be introduced to Einstein's mass energy equation, although you probably know it already, E equals mc squared, to consider the amount of energy that's released in a fusion or fission reaction. And you will also look at how to express this energy that's released in these reactions in joules, but also in evolts and a new unit, mega evolts. We're also going to talk about a different way of expressing mass, not in kilograms, but in unified mass units. So I'm going to start with that. A unified mass unit is a way of describing very small amounts of mass. So 1U will be used instead of 1.6605 times 10 to the minus 27 kilograms. In the data booklet, this is expressed as 1.66, and it's defined as 1/12 of the rest mass of an unbound atom of carbon-12. Approximately, it's the mass of one nucleon. If we think of protons and neutrons separately, we can see that there is a slight difference in mass, and you can see the mass is here. How do we express the mass of a proton? We can either describe it as having a mass of 1.673 times 10 to the minus 27, or we can say it's 1.007276 U's. Similarly, a neutron can be expressed in this way, and an electron can also be expressed. Any atomic particle can be expressed using the U notation. Now I want you to do a quick exercise. A helium nucleus is made up of 2 protons and 2 neutrons. I want you to now make one and tell me what the mass of a helium nucleus would be. That means add up 2 proton masses using this notation and 2 neutron masses using this notation. Stop the video and work it out. What you should find is that you get a mass of 4.031852, more or less, U's, right? That is the mass of these components together. But the actual mass of a helium nucleus is this, 4.001506 U's. There is a difference, which is weird, right? There shouldn't be any difference. If you take this mass and put it together, it should give you this mass, but it doesn't. So what we have here is a missing mass, and this missing mass is called the mass defect. Einstein postulated that the missing mass is converted into pure energy. So if you can work out this mass difference, you can then calculate the amount of energy that's given off. What's special about this energy is that it's called binding energy, and it's the energy that holds the nucleus together. So the mass defect is the difference in mass between the individual masses of the nucleons and the mass of the nucleus. Very important definition. Using E equals mc squared, we can work out the binding energy, the energy needed to put the nucleus together. So E, the binding energy, delta M, the missing mass, the mass defect, and C is the speed of light. So calculate the binding energy of a nucleus of nitrogen-14. Stop the video and work it out now. Now you should have had a missing mass of 0.108513. That's in unified mass units. Because we are going to be using the speed of light 3 times 10 to the 8, which is in meters per second, we need to convert this into SI units. So the first step is to multiply that by 1.66 times 10 to the minus 27. This number. Once we have that in kilograms, we can use the mass times the speed of light squared to give us the energy. And that will give us our answer in joules. Now, This is a very small amount of energy, and the appropriate unit to use would be evolts. So you divide this number by 1.6 times 10 to the minus 19 to give you your answer in evolts. And you would divide it again by 1,000,000 to give you the answer in mega evolts. Got that? Divide by the charge on an electron, 1.6 times 10 to the minus 19, and then divide it by 1,000,000. What does this do? This gives you the same energy, but in a new unit called the mega evolt. And so here we should find that our energy value in joules corresponds to 101 mega evolts. That process does seem rather complicated, and the IB gives you a shortcut. 1 U actually corresponds to automatically 931 mega evolts. And so you have this conversion in the data booklet. 1 U is equal to 931 mega evolts. And so when you have a question like this one, you can use that conversion directly. This multiplied by 931. Now try and do the binding energy in mega evolts of a helium-4 nucleus. If you use the immediate conversion, you should be able to get 28.2 mega evolts. Okay, once you've done that, you can now try the assignment.